In this video, we'll discuss Markov-Chain-Monte-Carlo, or short MCMC, which is a general set of methods for sampling from intractable distributions in machine learning in general, and also in particular in our context to sample from the posterior distribution of the weights in a Bayesian neural network. There are entire courses in MCMC, but in this short video, I hope to be able to provide a good overview. Now let's dive right in. Markov-Chain-Monte-Carlo. Markov-Chain-Monte-Carlo, or short MCMC, is a framework for sampling from an intractable probability distribution. Let's get started with some intuition. The problem that MCMC addresses is as follows. Given a probability distribution, P target, that we can evaluate only up to a normalization constant, we would like to draw samples according to this probability distribution. And in our case of Bayesian neural networks, this probability distribution is going to be our posterior of the parameter theta given the data d. The way that MCMC does this is to move along a chain of values of theta according to a so-called proposal distribution. For example, a local Gaussian. Then we accept improving moves, and worsening moves we only accept with a certain probability. Let's visualize these concepts. So starting from some point, let's say here, we first compute the proposal distribution. So this could be, for example, a Gaussian centered at the current point. And we sample from this proposal distribution. Let's say we go here, and then evaluate the target distribution up to a normalization constant at this point and at the previous point. We see that at the new point, the target distribution has a higher value than at the previous point. So we make this move. Our chain moves from this point over to that point. And then we iterate. So we first compute a proposal distribution that is now, in this case, a Gaussian centered around this new point. Let's say we sample from it again, say maybe in this case here. This is again an improving step. So we take a move, we take another sample, and then let's say we have another proposal distribution and we sample from it, and it's, say, over here, our sample. And this sample now has lower value under the target distribution than this previous value here that we had. And so in that case, we only accept with a certain probability. Let's say in this case, we accept again. Then we take another step. Maybe, although we don't have to move in one direction, these samples from this local Gaussian could also be on this side, of course. In this case, this would be an improving step. So we would take this step for sure. And then let's say we sample again. Now we sample this point. This point here now again is worse than that point over here. And let's say in this case, we don't actually accept, but we stay with our previous point. So I'm going to visualize this by saying we have another second sample here. Then let's say we draw another sample. Let's say this one is here. Let's say even though it's worsening, we accept. We draw another sample. Let's say it's over here. That's improving. So we accept. And then let's say another sample over here. And we accept. And then we can also this way explore the second mode of this distribution. And so we would have a sample here, and a sample here. And in the end, after we've done this a lot, and in practice this would be running for thousands or millions of steps, we keep a history, so the chain of our visited states. And in particular, we basically count. We have a sample right here, then we have one there, we have one there, we have two here, We have one there, one there, one there, one there, and one there. And this would then be our sample-based approximation of this probability distribution. Now you see that based on these 9 samples here, this is not a very good approximation yet, and you would need a lot of samples, like in the thousands or millions, to even have this very simple target distribution here be approximated very tightly. So I just mentioned that we keep this history, this chain of visited states. And that's a chain in Markov-Chain-Monte-Carlo. The Markov in the name comes from the fact that the proposal distribution only depends on the current state and does not depend on the history of how we got to it. So the future is independent of the past given the present. And the Monte Carlo in the name comes from the fact that we use a sample-based, a so-called Monte Carlo approximation of our probability distribution. So this was the intuition for MCMC. We start somewhere in our space of parameters theta. We use a proposal distribution in order to move along this space, accepting improving moves and only accepting worsening moves with a certain probability. And we keep a history, this chain of visited states, and that chain we use later on in order to build our Monte Carlo approximation of the probability distribution we want to sample. Now, having seen this intuition, let's look at this a little bit more formally. The key idea of MCMC is that you have a chain of samples going from theta t to theta t plus 1 to theta t plus 2 and so on, such that the samples in this chain converge to the target distribution p-target. You typically don't use every single element from this chain, but rather only use every tth sample, starting at some sample with a number k. So for example, if you have k equal 50 and t equal 10, then the subsample of the sequence that we would use is theta 50, theta 60, theta 70, theta 80, and so on. So here, throwing away the first k-1 samples is useful to reduce the dependence on where you started the chain. And the reason that after that you only take every tth sample is that you typically have a proposal distribution that is quite local, and if you were to take successive elements of your chain, then they would have highly correlated samples. Rather, if you wait t-1 steps in between, then the successive samples that you take are actually much less correlated. And then when we take a histogram of the sequence, then it approximates your target distribution. It would also approximate it if you used a smaller t or a smaller k, but, well, these are hyperparameters you get to choose to actually get a better approximation. Now, we can also use the sequence to actually approximate expectations of a function that depends on theta. And we do this expectation with respect to our target distribution. And so we simply do this expectation with respect to the target distribution by summing the function evaluations of f at our samples and then normalizing by the number of samples. I would also like to give you one slide of theory for MCMC to show you when this is actually guaranteed to work. That means guaranteed to sample from your target distribution. The ingredients here are a state space theta and a transition distribution that gets you from a state theta 1 to a state theta 2. Now this transition distribution has to be a probability distribution. So for each value of theta 1, the probabilities of the successor states going from theta 1 to theta 2 have to sum to 1. And this transition distribution combines the proposal distribution and the probability of accepting the proposal. For instance, the transition distribution probability to go from theta 1 to theta 2 is simply the proposal distribution to go from theta 1 to theta 2 times the acceptance of moving from theta 1 to theta 2. Now we would like our chain to sample from a so-called stationary distribution pi. And what it means for a distribution to be stationary is that once you're sampling from the stationary distribution, then you're staying in it. So you're not sampling the same element all the time, but the distribution that you're sampling from, that remains the same. Now formally, you can write this as follows. So for all successor states, theta 2, when you sum over all the predecessors, theta 1 of theta 2, and you multiply the stationary distribution of theta 1 with the transition function going from theta 1 to theta 2, then what you end up is the stationary distribution for theta 2. Now, if that property holds, then no transition along the proposal distribution can ever take you out of this stationary distribution again, because when you're in a state with stationary distribution theta 1, so pi of theta 1, and you follow the proposal distribution and the according transition distribution to go to theta 2, then you get to theta 2 with a stationary distribution pi of theta 2. And naturally, we don't only want the chain to sample from a stationary distribution, but we also want the stationary distribution actually to be our target distribution that we want to sample from in the first place. Unfortunately, such a stationary distribution does not always exist, but we can write down a sufficient condition for it to exist. This condition is called detailed balance. And detailed balance says that the probability for actually being in a state theta and transitioning to a state theta prime must be the same as for being in theta prime and transitioning back to theta. Now formally, the stationary distribution for theta times the transition probability going from theta to theta prime equals the stationary distribution of theta prime times the transition probability going from theta prime to theta. So if this detailed balance condition holds, then you know that there exists a stationary distribution. So having seen some theory about the stationary distribution, now let's actually talk about some practical issues. So unfortunately, even if we satisfy this detailed balance condition, and then we know that there is a stationary distribution, then it might still take a long while until we actually can sample from the stationary distribution. So it really matters where we initialize our chain. And the time it takes until this happens, that we're actually sampling from our stationary distribution, that is called the mixing time. And intuitively, you can think of this as the time until the chain forgot where you actually started it. If you have a complex multimodal distribution, then it might actually take some time until the sampling process actually forgets where it started. Whereas if the distribution is simple and unimodal, then this doesn't take very long. In practice, unfortunately, this mixing time isn't known. And in order to get around that, we typically start taking samples from the chain not directly at the beginning, but only after a so-called burning in phase. And optimally, you would like to set this burning in phase to be the mixing time, but you don't actually know the mixing time, so you need to set it heuristically by a hyperparameter. And in order to show that this mixing time is sometimes quite different, here are 3 different chains on different target distributions. So here on the left, there is a simple unimodal distribution, and the chain mixes really well. Then here in the middle, the distribution is slightly more complex with correlations between these two dimensions here. And we already see that the chain hasn't yet explored much of these low probability regions here at the top left and lower right. And finally, here on the right, we have a multimodal distribution. And actually, the chain has explored this first mode really well. And one could even think, if this part wasn't there, that it has even mixed already on that part. But it hasn't even touched the second mode yet. And in practice, well, you don't have the plots of the true distribution here. You only can take some characteristics of your chain, and the characteristics of this chain here look actually quite similar to the characteristics of this chain, because, well, it's just exploring one mode locally. So it's very hard to distinguish these two just based on these characteristics and diagnose that in the left case, we have actually mixed already, and in the right case, we're very far away from it because we haven't even seen one of the modes yet. Here we have a one-dimensional Gaussian mixture model with 3 partially overlapping components, whose true probability density function is shown as the red curve in these plots here. Now we sample points according to this distribution using MCMC, and the blue histogram in these plots indicates the density function reconstructed from the sampled points. In the left figure, we sample points before the burn-in phase, and we can see that the reconstructed density is very different from the true distribution. Whereas in the right figure, the points are sampled after the burn-in phase, and it can be seen that the reconstructed density approximates the true density very well. Now in this example here, we now have a 2D Gaussian mixture model with 2 components, plotted as a heat map where the brighter parts indicate regions with higher probability. And again, we use MCMC to sample points from this 2D Gaussian mixture model, and on the left, the points are sampled before the burn-in phase, and on the right figure, after the burn-in phase. And in the left, we see that our samples only explore this one mode of the Gaussian mixture model, whereas after the burn-in phase, they actually explore both of the components. So now I would like to tell you about the most famous MCMC algorithm of all time. This is almost 70 years old now. It's from 1953. It's called the Metropolis-Hastings algorithm. And this is actually often featured in lists of the most important algorithms in all of computer science. So the ingredients of this algorithm are a proposal distribution, here called G, for generating new states, and you're actually free to define any proposal distribution that you want. And then you have this acceptance ratio, A, and the transition probability is then just the proposal distribution times the acceptance ratio. Now, the important thing in Metropolis-Hastings is that you define this acceptance ratio in a way that guarantees that you always satisfy detailed balance. And Metropolis-Hastings does so by incorporating the target distribution into the acceptance probability, both for the state that you come from and the state that you're going to. And it also incorporates a proposal distribution going from the state you're coming from to the state you're going to, but also backwards. And this way, you're guaranteeing that you satisfy detailed balance. And I'll leave it as an exercise for you to actually prove that if you use this acceptance ratio, then you always satisfy detailed balance, regardless of which proposal distribution you use. So that's cool. You can then actually tune the proposal distribution. You can use the one that mixes the most quickly, and so on. The full Metropolis-Hastings algorithm is actually really trivial. So you start from some initial theta 0, for example at random. Then you generate a next candidate according to the proposal distribution that you choose. and you accept it with this acceptance ratio that we just talked about. And that's it. You simply iterate these steps indefinitely, and this algorithm will then, at some point, start sampling from the target distribution, because that is a stationary distribution of this algorithm by design. So Metropolis-Hastings was an example of an older MCMC algorithm, albeit really famous, but there are also newer MCMC algorithms that pertain more to neural networks. The big problem with MCMC algorithms for neural networks is that MCMC doesn't actually typically scale well to high dimensions. And that's typically because the proposal distribution is quite random and unguided. Often it's just a random sample in the vicinity of your current data point, for example, from a Gaussian, as we saw before. And that won't get you very far in actually finding good instantiations of neural networks. From training neural networks, we know that we really have to follow the gradient information in order to get to the good parts of their response surface. And these gradient-based updates can actually be put into MCMC algorithms as well to speed them up. In particular, there are these algorithms called Hamiltonian-Monte-Carlo that do actually take into account gradients, and a special case of these are so-called Langevin dynamics. In Langevin dynamics, we take a gradient of our log prior and a gradient of our log likelihood, and we multiply that with a learning rate, and then there's a secret sauce. We add some random noise. And this random noise comes from a Gaussian distribution. The interesting thing here is that if we do that and we set this random noise to the right size, then we can show for this algorithm that it will sample from the target distribution. So this is a good example of an algorithm in machine learning that takes pages of math to derive, and then out comes a one-liner. You just add some noise to your gradient step. Nevertheless, these Langevin dynamics as such are still slow because this log likelihood up here depends on the full data. So you take gradients of the log likelihood of the entire data set, just like we did in batch gradient descent. And well, you can actually speed this up by considering mini batches just as you would in stochastic gradient descent. And this then yields stochastic gradient Langevin dynamics, SGLD. And lo and behold, SGLD is almost identical to SGD. It just adds this Gaussian noise term. I can't go through the derivation here because this is very math heavy, but this actually works in samples from the stationary distribution. And in our case, that stationary distribution is a posterior distribution of our parameters theta given the data. And you can use this then very much like SGD, but it won't only give you a single neural network, but also a chain over neural networks that you can take samples from and get uncertainty estimates. So if you would like to see the derivation, it's in this paper here. And this trick of using mini batches also works in general Hamiltonian-Monte-Carlo algorithms, HMC algorithms, giving rise to SGHMC, stochastic gradient Hamiltonian-Monte-Carlo. We've also used this algorithm and extended it a bit with adaptive learning rates to get a Bayesian neural network that we can use in Bayesian optimization. And that's precisely where this plot here on the right comes from that I showed in the beginning, where the uncertainty grows nicely away from the data in these regions here, but is really low in the regions where you have lots of data here. And this is possible because this is just a well-calibrated Bayesian neural network. And this is also efficient because it uses stochastic gradient Hamiltonian-Monte-Carlo. So this is a very active area of research, and I certainly wouldn't claim that this is all said and done. SGHMC works great in some of our experiments, but it can also be very brittle in terms of setting its learning rates and other hyperparameters right. So there's a lot more to be done in order for this to really work out of the box. Okay, so to summarize this slide here, you can speed up MCMC by using gradients in one of various ways, and this is really important in order to get it to work for neural networks because of their really high dimensionality. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.